Can you believe it? We are on our third unit. This is so exciting. This is the disembodied voice of Mr. Larkin, and I'll be guiding you through Unit 3. Unit 3 is exciting because we've learned about atoms, we've learned about the sun, but depending on who you talk to, we haven't really learned any chemistry. Because chemistry is all about how chemicals interact and how they use energy. And we've really been talking about atoms. We haven't been talking about what those atoms do when they start interacting with each other. Well, that's what we're doing in Unit 3. So we're going to learn a little bit more about the periodic table, and then we're going to use that information to be able to predict and to explain how atoms actually bond to each other. I'm excited. So once again, I'd recommend using some roles. This is a good time to maybe pause and determine who's doing what, if you're making any changes, or if there's any new roles that you need to roll out. Haha. In any case, there's only 2 standards this unit. I know the other ones had 3. This one has 2. First standard is I can explain patterns on the periodic table and use them to predict properties of various elements. There's a lot of different patterns. We're going to talk about electron activity and atomic radius. Those ones are a little bit more complicated to explain. And then there's other ones which you just kind of got to memorize. Element type, family, valence electrons, etc. In standard B, I can describe how and why atoms form covalent, metallic, or ionic compounds. Those are the 3 types of bonding we'll learn about, and can explain the properties of those bonds. All right, let's start with something to get us a little curious. So what elements from the periodic table or materials do you think are in a smartphone? And what do you think each element is used for? Go ahead and take a little time on your own first, maybe a minute or 2, and then compare with your partners and cold call on people, call whole class, have a little whole group discussion. All right. Now, this could be whatever. There's any correct answer, but I imagine some people said metals for maybe conducting or something like that. Maybe you identified what the case is made of, maybe what the screen's made of. I'm sure it was an interesting discussion. Now you might have already been looking at this picture, but I want you to take some time to do observations and questions. So if you don't want to look at the picture, feel free to just kind of smash your phone on the ground and crack it open. Whichever one's better for you is fine. And then, don't do that, please don't do that. And then go ahead and do at least 2 observations, at least 2 questions about your observations about this broken down phone. All right, you pair shared, you discussed as a whole class. So what are some things you might have noticed? Well, I notice there are electronic pieces, circuits and things like that. There's a battery and a screen. I don't know, the inside has a lot of gray with some shiny / gold pieces. Oh, I wonder if that's actually gold. Maybe that's why phones are so expensive. Oh, a big chunk of what's inside is the battery. I mean, the battery, that's like 1/3 of the space inside the phone right there is just that battery. I notice it says Li ion. I'm wondering, is Li lithium? So is that gold? Is the battery lithium? What's an ion? You know, is that like an atom? What's going on there? What's the screen made of? You know, because it's like you can touch it. So is it normal glass? Is it special? What's going on there? What's the gray pieces? Why use the things they're using in the phone? That's a really general question. But like, why Li? You know, why use shiny stuff? If it is gold, right, why gold? Because gold would be like the most expensive choice you could pick, you know? Like, why not pick something else? Copper or something like that. All right. Well, you might have had some other ones as well, but You probably said something similar to me, I hope. Let's keep going. So standard 8. This is our first one. Again, there's only 2. It says I can explain patterns like electronegativity, atomic radius, element type, family, and valence electrons on the periodic table and use them to predict properties of various elements. So there's a lot of basic information. It seems like a lot. It's 2 pages of a reading. That's it. There's just a lot of little things. So I would recommend maybe doing some flashcards or maybe quizzing each other or do whatever you got to do. The homework's going to help a lot, so make sure you're always doing the homework. It always helps, but especially for memorization, stuff like this. So you need to know all of this, which is on the periodic table. You really just need to know where they are. So groups, periods, metals, semimetals, nonmetals, and then families, alkali metals, alkaline earth metals, transition metals, halogens, and noble gases, which are also called inert elements. And then you need to know properties, which are like characteristics of metals and nonmetals. Turns out metals are conductive, malleable, and shiny, and nonmetals are the opposite. Instead of conductive, they're insulators. Instead of malleable, they're brittle, and instead of shiny, they're dull. You also need to use the periodic table to find the number of electron shells and the number of valence electrons. We actually learned how to find the number of valence electrons from the periodic table already in Unit 2, but we didn't really practice it, so we'll cover that again. And then you need to know that families react similarly because they have the same number of valence electrons. Moving on from kind of the basic periodic table stuff, you need to know about electronegativity and atomic radius, what they are. You need to know what the patterns are on the periodic table. Turns out there's very predictable patterns for these 2 properties on the periodic table. And then you need to be able to explain them in a period, which is horizontally on the periodic table, and then in a group, which is vertically based off protons or electron shells, depending on which atoms you're comparing. So let's start off by reading some basic information about the periodic table. As always, when we do our readings, you can follow along with me. You can also do a partner read or do it individually, although I would recommend, after you do a partner or individual read, maybe still play the guidance video and do a second read so that you can kind of hear it again and also get my guidance. So here we go. The periodic table: metals, nonmetals, and semimetals, and family names. The elements in the periodic table are organized from low to high atomic number. The average atomic mass generally also increases, although there are some exceptions. There are 3 main types of elements in the world: metals, semimetals, and nonmetals. Metals are shiny elements that can conduct electricity. They're also malleable, which means they're easy to bend. Or, not always easy, but if you put enough energy into them, instead of breaking, they bend. Metals can be found on the left side of the periodic table. Nonmetals are the opposite of metals. They are called insulators, which means they cannot conduct electricity. Nonmetals are dull and brittle, which means they snap instead of bending when enough force is applied. So think of something like your pencil lead. Pencil lead is made of carbon. It's pure carbon. You really can't bend it. Maybe a tiny bit, but then if you try to bend it like a paperclip, it just snaps. Whereas a paperclip is metal, so it's malleable. Whereas pencil lead is a nonmetal, which is brittle. Found on the steps in between nonmetals and metals are the semimetals. As their name suggests, these elements share properties that are in between nonmetals and metals. Figure 1 shows the distribution of metals, semimetals, and nonmetals in the periodic table. So on the periodic table, there's a little kind of staircase. A lot of periodic tables actually have it bolded. Hopefully yours does as well. And on that staircase is where the semimetals are. Basically, if it touches the staircase, it's a semimetal, with the exception of aluminum, which is a metal. So anything to the left of that is a metal, except for hydrogen, which is a nonmetal, along with everything to the right of the semimetals. So as a couple examples here, if you took argon, argon's a nonmetal, we would expect it to be an insulator, and it is. It does not conduct electricity. Whereas if you took something like iron, Fe, we would expect iron to be a conductor. Electricity can flow through it, and sure enough, it does. Moving on. The periodic table is organized by rows and columns. The rows are called periods and correspond to how many electron shells an atom has. The columns are called groups and correspond to how many valence electrons an atom has, skipping the transition metals. See second figure below. Well, let's look now. Number of valence electrons. Okay, so I guess this is the ones they're skipping, so that must be the transition metals. So all of these have 1, all of these have 2, all these have 3, 4, 5, 6, 7, 8. Within the general categories of metals, semimetals, and nonmetals, there are specific names for some families, which are groups. Because groups all have the same number of valence electrons, they tend to react in very similar ways, like a family in real life might. And this is where you go, I'm nothing like my parents. No one understands me. I'm a teenager. This might be true. But when you turn 30, you look in the mirror and you go, whoa, how did I become my mother or father? Since group 1 all have 1 valence electron and react similarly, they're called a family. Figure 2 has the names of each family labeled. Inert elements are also called noble gases. When you hear me talk about them, I'll always say noble gases, because that's how I was taught. You should memorize the alkali metals, alkaline earth metals, transition metals, halogens, and noble gases. All right, let's see if we can find them. So here on the left, we've got alkali metals. Notice hydrogen, which is the first element, is a nonmetal, so even though it's in group 1, it's kind of a weird, odd ball. It doesn't really fit well anywhere. But it has 1 valence electron, so it's here. But it's not a nonmetal. But it's also not a halogen, so putting it here would be weird. And then there's the alkaline earth metals. Transition metals is a big block in the middle. We're not going to talk about their valence electrons, so don't worry about that. That's why you skip it here. They have something else called oxidation states, but it turns out they react more alike than they do different, even though they have different oxidation states and things like that. So that's the transition metals. And then the halogens is over here, fluorine, chlorine, etc. And the noble gases are over here, neon and helium and whatnot. The lanthanide and actinide series also have names, but I'm not going to have you memorize those. Just these 5, boom, 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 are the only families I'm going to demand that you learn. Notice the electron shells is also something you can pick up. So like, for example, sodium's right here. It has 3 electron shells, whereas lithium's right here. It has 2 electron shells. And then remember the valence electrons. So that's it for basic information on the periodic table. You need to memorize this really before you even move any farther into the notes, because I'm going to talk about all this as if you understand it. It's a lot of little things, but let's practice it right now. So here I've got a basics practice for the quiz. So there's 20 questions, I think. Yep. And if you scroll, well, you can't scroll. Well, maybe you can. I don't know. Are you online right now? Anyway, if you turn to the back of your notes, there is an answer key. Don't look yet. Why are you looking? Oh, ridiculous. No cheaters. But go ahead and take some time and fill in all these blanks. So, for example, potassium is part of the blank family. Well, if you look for potassium on the periodic table, and I know this one doesn't actually say it, but potassium is right here. So that means it's an alkali metal. So we'll just take this and we'll write alkali metal family. It's not the alkali family. It's not the it's not the alkali metal family. That's the second group. It's not just alkali. It's not just metal. It's alkali metal. So make sure you say the names actually correct. Otherwise, you know, it's like calling me Mr. Larking. And, of course, I am a king. But it's Mr. Larkin, the disembodied chemistry teacher voice, not Mr. Larking. All right, so go ahead and take some time and work together. There's 20 questions, so maybe 15 minutes because they're pretty basic. And then I think it would make sense to go over the answers as a whole group. All right, let's go over these answers. So we already went over potassium. Potassium is part of the alkali metal family. Boron has 3 valence electrons. How do we know that? Because boron is right here, and if you count the groups, it's 1, 2, skip the transition metals, 3. So that's 3 valence electrons. Chromium has 4 electron shells. Chromium is right here, so it's in the 4th period, 4th row down, so that's how many electron shells it has. Iodine is a halogen. It's in this group, right there, iodine. Helium is a noble gas. Which element has 4 valence electrons and 2 electron shells? So 2 electron shells would be row 2, period 2, And 4 valence electrons would be 1, 2, 3, 4. The fourth group over, skipping transition metals. So that's carbon. What's the name of the family in the middle? It's a transition metals. If an element's in the same family as another one, they react similarly because they have the same valence electrons. Metals all likely conduct electricity. Nonmetals are likely to be an insulator. They do not conduct electricity. If an element is a semimetal, it will have properties in between metals and nonmetals. What is the last member of the noble gases? So if you put this one, oganesson, that's fine. I put radon because oganesson is man-made and it's so radioactive it lasts less than a second. So as far as like actually getting any, we actually don't know what it acts like. Like, does it actually act like a noble gas? We expect it to. It should. But you never really know until you test it. Like, aluminum's a metal, not a semi-metal, even though based off its position, we would expect it to be a semi-metal. Well, oganesson's also kind of in between. Like, it's on that staircase, so I don't know. What is it? So either one is an acceptable answer for the purpose of this quiz. Practice quiz. Lithium has 1 valence electron. How do we know that? Because it's in the first group, right there. 1 valence electron. The period determines the number of electron shells. We've been doing that. The group, which is the column, determines the number of valence electrons, with the exception of the transition metals. Selenium has 4 electron shells, because selenium's right here, which is in the 4th period. Calcium's part of the alkaline earth metal. That's right here. Not alkali, alkaline earth. Although I have seen it a couple times as alkali earth, so I guess we would have to accept that. But most textbooks call the first one alkali metal, and then the second one alkaline earth metal. And 18, sulfur will likely snap instead of bending, which means it is brittle. The transition metal family don't exactly have valence electrons. They have oxidation states. And metals are malleable, which means they bend into a new shape instead of snapping. So there you have it. So that's already like a third, maybe even half of that standard. It's just memorizing all that basic stuff. Now, let's start moving into the more fun stuff, I think. So we're going to start by looking at 2 of the families, the alkali metals family, and then on the second half of the page, the halogens. So it turns out the alkali metals in group 1, they all react with water. And when they react with water, they produce hydrogen gas and heat. Depending on how fast metals lose electrons, they react faster. So here's an example chemical equation. 2 lithium atoms plus 2 water molecules combine to form 1 H2 and 2 LiOHs. The symbols in parentheses are their phases. So solid plus liquid creates a gas, and then aqueous, which means dissolved in water. And notice they're also producing heat. So my question for you is, of the alkali metals, which do you think is going to produce the most hydrogen and heat, and how come? So go ahead on your own first, pause the video, and then pair up and discuss as a whole class before unpausing. Alright, so what did you guys say? Now generally, what I found is that people pick one of the 2 extremes. Remember, hydrogen is not an alkali metal, so people pick either lithium or they pick francium for various reasons. They think francium, oh, it's big, so bigger is better, and then lithium because, it's not very heavy or it doesn't have very many electrons, even though they have the same valence electrons. There's lots of possible reasons. But let's actually figure out which one reacts fastest. So I've got a video. The video, it sounds ancient. I don't know when it was, but it's fun. So go ahead, watch it, and what can you conclude about the reactivity of metals as you go down the periodic table? So pause mine and watch this one. Alright, so they only got to cesium, but that was interesting. So the cesium just straight up exploded, right? It started off with lithium just kind of bubbling, and then at the end, cesium just shatters the whole glass. So it definitely seems like as we went down the periodic table, the alkali metals reacted faster and faster. So therefore, all metals perhaps react faster as you go down. All right. So let's look at halogens now. So we're on the other side of the periodic table. We were in group 1. Now we're going over all the way to group 7A or 17, depending on which numbering system you use. So they can all react with aluminum. They form aluminum halides and they release energy in the process. So both of these are exothermic, which is something we'll learn in the next unit. They release energy. So it turns out the faster halogens gain electrons, the faster they react. So not losing electrons this time, the halogens are gaining them. So here's an example reaction. 3 molecules of F2, that's fluorine, gas, react with aluminum solid, and they produce aluminum fluoride, AlF3, and heat. 2 of those. So I want you to make a hypothesis again. Which halogen will react fastest and produce the most heat? Go ahead, pause the video, make a hypothesis. All right. So now let's figure out if you're right. Watch the video and answer the question. What can you conclude about the reactivity of nonmetals as you go down the periodic table? All right. Well, that one was a little harder to tell because they were all different phases, right? The fluorine and chlorine were gases, but then the iodine was kind of a solid and bromine was a liquid. But it seemed like the fluorine and aluminum, it was just a flash and it was done. So it seemed to react the fastest. And then the other ones, they had to like heat up. So those ones, they kind of cheated, you know? It's like they were so slow that nothing would have happened unless they added heat. So what can you conclude? So I would say that the nonmetals seem to react slower as you go down the periodic table, since to make the reactions work, heat had to be added to speed it up. I guess it kind of makes sense because nonmetals and metals are opposites, so metals react faster as you go down, whereas nonmetals slow down as you go down. So now the question is, why is that? Like, why are there those patterns? And we're going to explain the patterns that we saw in the videos through something called atomic radius and electronegativity. So on this page, I've got definitions for you. So let's just go ahead and go through these definitions. Atomic radius, it says the distance from the nucleus of an atom to its valence electrons, the atomic size. It's essentially how big the atom is. Remember, from geometry, a circle is this round thing, and the radius is the distance from the center to the outside. Well, in a nucleus, or in an atom, the nucleus is the center, and the outside is the valence electrons. So then the atomic radius is the distance from the center, the nucleus, to the outside, the valence electrons. In this example, this would be a small radius, this would be a large radius. So larger radius, larger atom. Electronegativity is a measure of how strongly an atom attracts electrons. A higher electronegativity means that the atom attracts electrons more. A lower electronegativity means that the atom attracts electrons less. If you need to, you can pause and practice saying this word. I don't want you to say You are fully capable of speaking the language of chemistry. If you need to practice, that's perfectly acceptable. But don't give up and don't cop out. Electronegativity. I mean, it's only, what, 17 syllables? You can do it. So here's an example of electronegativity. The figure shows that fluorine pulls electrons more towards itself because it says electron density, so there's more electrons than this side. So this would mean that fluorine has a higher electronegativity because the electrons are being pulled more to fluorine than hydrogen. Essentially, electronegativity is how good an atom is at attracting electrons. If you need an example, just remember Mr. Larkin is very electronegative. That just means I'm very attractive. I know you can't see me, but you'll just have to take my word for it. I'm very attractive. That's why I don't show my video, because otherwise you'd be too distracted. You get it. You get it. All right, here's some practice questions. Go ahead and pause. Spend some time working with your partner, and then unpause to go over the answers. All right, we spent some time working on these. Let's go over the answers. Number 1, recall the relationship between electromagnetic force and distance to the left. This was from Unit 1. Which would you expect to have a greater attraction to a nucleus, an electron close or far away? So the farther away you are, the lower the magnetic force, so I would expect the one closer to have a greater attraction. The closer electron will feel a greater force because as the distance decreases, the force increases dramatically according to the graph. Based off your answer number 1, would you expect a large atom to have a high or low electronegativity? Electronegativity is how well an atom attracts electrons. Therefore, I would expect the small atom to have a higher electronegativity because if the electrons are closer to the nucleus, they should feel a greater attractive force. If an atom with a high electronegativity and an atom with a low electronegativity both try to attract the same electron, what would you predict would happen? This reminds me again of my beautiful self. So I'm married, and it turns out in college, my wife was highly sought after. I mean, just in 1 month span that I'm thinking of, she had like 3 friends ask her out because she was just too nice and very good looking. But who ended up with her? That's right. The more attractive guy, me. So I think the same thing would happen here. If a high electronegativity atom and a low electronegativity atom both try to attract the electron, I would expect the high electronegativity atom to take the electron because the atom is stronger based on its electronegativity. Lithium is often used in batteries because the atom can move around more easily than other metals like sodium that react similarly. Which do you think has a larger atomic radius and why, lithium or sodium? Well, if lithium can move around easily, perhaps it is smaller. I mean, I don't know. Based off the information they gave us, I feel like that's all you can really say. It has a lower mass, but mass and size aren't the same thing. Mass is how heavy something is, whereas size is how big something is. They do tend to go together, but not always. All right, we've got some patterns here in the periodic table. So first we're going to look at period. So remember, period is horizontal. Put that on a flashcard, drum it into your head as much as you need to. Hopefully you already did. Periods are horizontal. So we're going to start by looking horizontally across the periodic table. It would help if you had your periodic table out in front of you. Notice the periods are labeled here. They have period 2, 3, 4, 5, 6. Period 1 is only 2 elements, so you barely see it. But you can look at some patterns in period 2 through 3, 4, 5, and 6. So what happens to the electronegativity and what happens in a group? So periods are easy. How do you find the groups here? Well, let's take group 1. So what's the first element in group 1? Can you find it? Circle it on this chart here. Can you find the second element in group 1? How about the third one? All right, let's do it together. So hydrogen's right here. That's the first element in group 1. Lithium's the second one. Then sodium, then potassium, then rubidium, and then cesium. And then they stopped at period 6, so we don't have francium here. All right, so you should be able to use this pattern right here to answer the ones about a group. All right, go ahead and take some time on your own, then with partners. See if you can fill in these blanks. So generally, as atomic number increases in a period, the electronegativity seems to increase. So increases, which means that atoms attract electrons better or stronger, or however you want to say that. Generally down a group in the periodic table. So let's look at group 1. Electronegativity decreases, which means the atoms attract electrons worse. They are not attractive. So here we would expect hydrogen to be much better at attracting an electron than cesium would be. All right, let's look at atomic radius. So same thing. Let's look in a period and in a group. You can use the same strategy for groups that we did previously. Go ahead and try it. All right, so as atomic number increases in a period, it seems like the atomic radius decreases, which means that atoms are getting smaller. This is actually a little surprising because as you go to the right, they have more stuff. Like lithium only has 3 protons, neon has 10, but lithium is twice as big as neon. What? That's like adding air to a balloon and having it get smaller. I don't think that's something that can happen. If you can do that with a balloon, you should go on like a game show or something. America's Got Talent. Generally, down a group in the periodic table, so remember you can look at group 1, hydrogen, lithium, sodium. Atomic radius is increasing, which means the atoms are getting larger. Alright, so are atomic radius and negativity proportional or inversely proportional? So proportional means when one goes up, the other goes up. Inversely proportional means when one goes up, the other goes down. And it seems to me, well, why don't you actually go ahead and try it first? Did you discuss already? Come on. It seems to me they have the opposite pattern. Like if we look at period 2 here, the electron activity is shooting up, whereas here in period 2, the atomic radius is going down. It kind of levels off, but it goes down pretty steeply at first. So they are inversely proportional. When one goes up, the other goes down. All right. Let's do a little investigation before we do our reading. Let's see if we can maybe kind of figure some things out on our own. How can atomic structure explain the patterns in electron activity and atomic radius? Because we know a lot about the atom already. We know about the nucleus and protons and electrons, and we know about electron shells and neutrons and all that stuff. So let's see if we can actually kind of figure out an explanation here. So as a reminder, electron activity increases to the right on the periodic table and decreases going down. Atomic radius does the opposite and decreases to the right while increasing going down. Periods on the periodic table are horizontal rows. As you go to the right on the periodic table, electron activity increases and atomic radius decreases. This means that electrons are more strongly attracted and the atoms are smaller. Compare the two models below and answer the questions to try to determine why these patterns exist. So here the protons is going to be the one with the plus, neutron is a solid circle, and electrons are dash. So we've got lithium, atomic number 3, and nitrogen, atomic number 7. Notice nitrogen is a little smaller because as you go to the right on the periodic table, atomic radius decreases. But let's see if we can figure out why. So go ahead and answer these questions. Work on it with partners, discuss this whole class, and then you can unpause the video. All right, what are the charges of electrons, protons, and neutrons? Electrons are negative. Protons are positive. Neutrons are neutral, so they have no charge. What is it that keeps the electrons from flying out of the atom? Well, the electrons are negative, so the protons attract the electrons. How many protons does lithium have? How many does nitrogen have? Lithium has 3 protons, and nitrogen has 7 protons. Based off the pattern for electron activity, which element attracts electrons more? Nitrogen is more to the right on the periodic table, and so should attract electrons more. Why does nitrogen have a higher electronegativity? Well, that's the million-dollar question, isn't it? It seems like this is getting us to think about protons attracting electrons, so perhaps it's because nitrogen has more protons. And then since nitrogen attracts electrons more strongly, where do the electrons go? Well, if they're being attracted, then I would think the electrons would go towards the nucleus. Maybe that's why nitrogen is smaller. All right, that's periods. Thinking about protons attracting electrons. What about groups? Remember, groups on the periodic table are vertical columns. Going down a group, electronegativity decreases and atomic radius increases. Therefore, electrons are less attracted to the nucleus and farther away. Compare the two models below and answer the questions to determine why. So here we've got lithium again, but instead of comparing it to nitrogen, we're going to compare it to hydrogen, which is right above it on the periodic table. So hydrogen is actually smaller than lithium is, but why is that? So go ahead and work on these questions with each other, and then you can pause the video. What happens to the energy of an electron as it moves farther away from the nucleus? In Unit 2, we learned that the farther away an electron is from the nucleus, the more energy the electron has. Notice I couldn't say the more energy it has because I had nucleus and electron. It's unclear which one I'd be talking about. So I would recommend not using it. We're going to do a lot of writing for this unit. Don't use the word it, just ever. If you're an extremely strong writer, you might be able to get away with it, but I would recommend not. What is the definition of atomic radius? Well, that's just straight from the previous page. So atomic radius is how far the valence electrons are from the nucleus. Which electrons are the valence electrons? The valence electrons are the electrons farthest from the nucleus. They're on the last shell. How many electron shells does each element have? Hydrogen has 1 electron shell, and lithium has 2 electron shells. Why are lithium's first shell electrons closer to the nucleus? Okay, hold on a second. Let's look at these. So the first shell would be this one. And yeah, I guess if you compare hydrogen's first shell to lithium's first shell is actually a lot smaller. It's kind of interesting. So lithium's bigger as a whole, but the first shell of lithium actually is smaller. Well, I guess it'd be for the same reason that nitrogen is smaller than lithium. Maybe it's the number of protons. So lithium's first shell is pulled in by, or because, lithium has more protons to attract electrons. So then why is lithium larger? Well, lithium doesn't only have 1 shell. Lithium has 2 shells. So the electron in the second shell has much more energy and moves farther away, making lithium larger than hydrogen. If lithium's electrons are farther away, does the nucleus attract them more or less? Well, we know that when a charged particle is far away, it feels a weaker force, and so the electrons far away are not attracted as well in lithium. Let's try to cement this. So what we came to was that in a group, the electron shells seem to explain why there are more, or why the electrons are farther away and less attracted. And here in a period, the number of protons seem to explain why electrons are getting closer and more attracted. But let's go ahead and read and see if we can cement this understanding. So periodic trends, atomic radius and electronegativity. How do scientists explain the patterns in atomic radius and electronegativity that we have observed? As it turns out, scientists have been able to explain those patterns using only basic atomic structure. Within a group, which is going up and down on the periodic table, we can explain these patterns using the number of shells that an atom has. As we move down the periodic table, the atoms have more shells. As we move down the periodic table, each atom has more shells. Because of this, electrons are further from the nucleus, atomic radius increases, and electrons feel less attraction from the nucleus, electronegativity decreases. The more shells an atom has, the larger its atomic radius is, since each shell is larger than the previous. As the shells become larger, the electrons on the valence shell are farther and farther from the nucleus, so the electrons feel less attraction from the nucleus. This means that the electronegativity decreases. So essentially what was said right here, but explained in paragraph form. How about a period? Using our knowledge of the atomic nucleus and its surrounding valence shells, we can explain why the trends of atomic radius and electronegativity look the way they do across a period, which remember that's side to side. In a single period, all the atoms have the same outer shell, but different numbers of electrons. As we move to the right, more protons are added to the nucleus, even though no more electron shells are added. So that's important, no more shells. So here's period 2, looks like they're getting smaller and smaller and smaller, and it says number of protons increases. As we move across a period, each atom has more protons. Because of this, electrons feel more attraction from the nucleus, meaning electronegativity increases, and electrons move toward the nucleus, which means atomic radius decreases. From left to right, the atomic number increases, which means that the number of protons also increases. As more protons are added, the attraction between the nucleus and the outer electrons gets stronger, and the electronegativity increases. Since the attraction between them is now stronger, the outer electrons are drawn closer to the nucleus, shrinking the atomic radius. Let's do some practice on this. Number 1 and 2 you should do together, at the same time. Do it on your own first, then with partners, then discuss whole class. Alright, the most important factor to consider for periodic trends in a period is protons, and the most important factor in a group is electron shells. If you try to explain, the pattern in a period with electron shells, you won't be able to, because electron shells only change when you go up and down the periodic table. And then protons will give you the wrong explanation because electron shells, it turns out, are more dominant. Because as you go down, there's more protons, but it doesn't matter because the electron shells dominate. Number 3, comparing potassium and sodium, explain whether potassium is larger or smaller and whether potassium attracts electrons better or worse. In your explanation, which is going to be at least 2 or 3 sentences, make sure you discuss all 3 of these bullet points. Electron shells or protons, depending on if it's in a period or in a group. You need to talk about atomic radius and demonstrate you know that's the distance between valence electrons and nucleus. And you need to talk about electronegativity and understand that's based off attraction. Here, AR is atomic radius, EN is electronegativity. Do some extended time on your own before you pair up and before you discuss as a whole class. I'm thinking at least 3 minutes on your own before you start to pair up. Alright, so you spent some time on your own. So let's go over this. That's weird. Alright. So first off, where are they on the periodic table? Sodium is right here, potassium is right here. So they are in the same group, which means protons are less important. Electron shells is what we want to use to explain this. And sodium's in the 3rd row, which means it has 3 electron shells. Potassium's in period 4, so it has 4 electron shells. So let's just start with that. Sodium has 3 electron shells, and potassium has 4. Since potassium has more electron shells, the electrons are farther away from the nucleus. The valence electrons specifically. The inner ones are actually closer, making the atomic radius larger. Since the valence electrons are farther away for potassium, potassium has a weaker electronegativity and electrons are not attracted as much. Okay, what is going on with my text box here? You know what, I'm just gonna delete it because at this point we already have the answer right here. Okay, we need to do the same thing for number 4 now with the same criteria. If you haven't done it already, go ahead and take some time, pause the video, and try it. We're going to compare sodium and chlorine this time, not sodium and potassium. Is chlorine larger or smaller, and does it attract electrons better or worse? Alright, you've unpaused the video. So chlorine's right here, sodium's right here. They are in the same row, that's period. So that means the most important factor is protons because they all have 3 electron shells in that period. So we're going to say chlorine has more protons than sodium, but the same number of electron shells. Therefore, chlorine is going to attract the valence electrons more strongly, increasing electronegativity. As the electrons are more attracted, they also move towards the nucleus, shrinking the atomic radius. I kind of did that in the opposite way that the question asked, but as long as the job gets done, I think it makes more sense this way personally, because it's the protons doing the pulling, and then it's because they're being pulled that the nucleus gets closer and they shrink. Alright, I got some extra practice because after this we're going to move into our next standard. So go ahead and take some time, work on this with each other, and then when your class is ready you can unpause to go over the answers. Number 3, what is a valence electron? How many do chlorine, calcium, lithium, and neon each have? You don't need Bohr models for this. What family is each group in? So that's just starting off with definitions. A valence electron is an electron located on the last shell farthest from the nucleus. Let's get this set up. Chlorine, calcium, lithium, neon. Alright, so chlorine is right here. So it would have 7, because 1, 2, skip, 3, 4, 5, 6, 7 valence electrons. Calcium is right here, so 1, 2, it only has 2 valence electrons. Lithium only has 1 valence electron, it's in that first group. And neon is all the way over here, so 1, 2, skip, 3, 4, 5, 6, 7, 8 valence electrons. So chlorine, 7, 2, 1, 8. What family group is each element in? Chlorine again is right here, so it's a halogen. Calcium is an alkali earth metal. What was the other one? Lithium is an alkali metal, and neon is a noble gas or inert element, would also be acceptable. So chlorine is a halogen, calcium, alkaline earth metal, lithium, alkali metal, neon, noble gas. How are metals and nonmetals different? Oh, let's make this red. Doesn't really matter. Metals conduct electricity, are malleable, and shiny. Nonmetals are the opposite and are insulators, brittle, and dull. So if you want to call someone boring, you can say they're dull, or you can be like, oh, you're acting like such a non-metal right now. Don't say I never helped you in life. There you go. Number 3, quickly define atomic radius and electronegativity. Atomic radius, the distance between the nucleus and valence electrons, electronegativity, how well an atom attracts electrons. Boom! Can I have another? Certainly. Why is bromine smaller than calcium? Wasn't that nice they actually told us? So let's find them on the periodic table. So bromine is right here. Calcium is right here. So they're both in period 4. And it said, why is bromine smaller? Yeah, bromine weighs twice as much. Has a mass of 79.9. Calcium has a mass of 40. So bromine is twice as heavy, but smaller. So why is that? So we're in a period. So that means we need to explain based off protons. We'll say bromine has more protons than calcium does. Therefore, the protons attract bromine's electrons better, pulling the electrons in towards the nucleus. This process shrinks the atomic radius and size of bromine. There you have it. Why does it take more energy to remove an electron from calcium than radium? Alright, calcium, we already know where calcium is. What about radium? Radium is right there. So they are in the same group. So to explain this, we want to think about electron shells, not protons. And if calcium takes more energy, I think that means calcium is stronger. So we're explaining why calcium is better at attracting electrons, essentially. Calcium has fewer electron shells than radium does. This means that the electrons are much closer to the nucleus for calcium and therefore more attracted. As the electrons are more attracted, they should take more energy to remove. All right. It's a new standard! So exciting! Remember, there's only 2 in this unit, so now we're halfway there! Although, yeah, I guess we're just about halfway through the packet, too. Yeah. Alright, standard 3b. I can describe how and why atoms form covalent, metallic, or ionic compounds and can explain the properties of those bonds. So you need to explain how electrons move when ionic, covalent, and metallic bonds form. You need to use something called Lewis dot structures, which are basically like abbreviated Bohr models, to show how electrons move when bonds form. You need to use electronegativity, which we've been talking about, to explain whether electrons are transferred, shared, or delocalized in bonds. You need to explain relative melting point based off how strong bonds are, and describe the melting points and conductivity of ionic, covalent, and metallic bonds. You'll also need to identify the structure of compounds as either crystal lattice, molecules, or malleable solids. Let's get right into it. Let's learn about something called the octet rule and ionic charge. The noble gases, remember that's group 8 or 18, depending on how you count, are a unique type of element. Table 1 below lists the formulas for how noble gases are found in nature versus how other elements are found in nature. After reviewing Figure 1, record your observations before reading further. Go ahead, take some time on your own. What do you notice? Well, one big thing I notice here is that the noble gases are all alone and the other elements all at least pair up with others. Even oxygen, if you look, oxygen is O2, but it's still 2 O's. It's not 1 O by itself. That's actually where the noble gases get their name, because they're too noble to mix with the peasant elements. You know, they keep to themselves like a medieval noble in a castle. The noble gases are unique because of how their valence shells are filled. Remember, valence shells are the last shell. What do you notice about the number of valence electrons in each noble gas's last shell? How many electrons can fit in their last shell? So here are the first 5 noble gases. What do you notice? Take some time on your own first. Alright, so this is a little tricky because they all have 8, but helium doesn't. Helium has 2, and then these ones all have 8. So what do they have in common? Well, what they have in common is you can't add any more. Because helium, it only has 2, but if you try to add one, it's its first shell. So that new electron will go into shell number 2. It won't go into shell number 1. So the noble gases all have full valence shells. Most of them being 8. Alright. Every atom is most stable when it has a full valence shell. The noble gases already have a full electron shell, and so they are very stable. The noble gases don't make chemical bonds with any other elements. They do not need to gain or lose any electrons because they already have a full electron shell. Since a full valence shell usually requires 8 electrons, this phenomenon is called the octet rule. Atoms can gain or lose electrons to get a full valence shell. Metals have a low electronegativity and will lose electrons. Because metals are losing electrons, which are negatively charged, they will become positively charged ions, which are called cations. Not cations, cations. Like cat, like meow, like the things that scratch you and kill birds. Cation. With charge equal to however many electrons they have lost. Nonmetals have a high electronegativity and will gain electrons. Since electrons are negative, nonmetals will become negatively charged ions, called anions, with charge equal to however many electrons they have gained. Here's an example of a metal and nonmetal forming ions to fill their valence shell. So metals, remember, they lose electrons to get a full outer shell. So sodium has 1 valence electron, but if you take it away, sodium has 8 now. So sodium has a full shell, not by gaining 7 electrons, because sodium is not nearly strong enough to do that, but by losing 1 and revealing its shell underneath. Whereas fluorine has 7 valence electrons, and remember the electrons are close to the nucleus, and so fluorine just grabs another one to form a fluorine ion. There should be 2 little dots right here. They look like they're cut off. Yeah, there you go. So it has 8 total. Lewis dot structures are shorthand for Bohr models that only show the valence shell of each atom. To draw Lewis dot structures for atoms, determine how many valence electrons the atom has. Add 1 electron to each side of the element symbol, top, right, bottom, and left, until you run out of valence electrons. So here's some examples. Potassium only has 1, so you just add 1 at the top. Bromine has 7, so you go 1, 2, 3, 4, and then you start pairing up. 6, 7, 5, 6, 7. Counted wrong. Sulfur has 6, so 1, 2, 3, 4, and then pair up. 5, 6. And then krypton has 8, so everything's full. Drawing them like this, as opposed to putting all of sulfur in 3 pairs, is going to make our lives easier later. Because basically what's going to happen is every electron that doesn't already have a pair is going to get a pair somehow. Because that would give it 8. So here's a criteria. If you didn't understand these 3 main concepts, then you need to go back before moving on as a class. So you need to know the octet rule, what it is and what it tells us. You need to explain ions and how they form, cation and anion, and you need to explain Lewis dot structures, and you need to be able to draw them yourself. Let's watch an experiment here. So we're going to look at magnesium and oxygen making magnesium and oxide. So basically we're seeing what happens when metals and nonmetals interact. So some background information. Many metals and nonmetals will react to make something called ionic compounds. These compounds have characteristic structures and properties. Go ahead and watch this video and record observations. Pause mine. All right, that was a lot. They got into a lot more than we're going to go into. They kind of went beyond this unit when they were talking about redox and things like that. But I just wanted you to see magnesium getting lit on fire. And they also did a good job of showing the magnesium oxide afterwards. So work through these discussion questions on your own first, then with a partner, and then unpause the video when you're ready. Alright, what type of element is magnesium? It is a metal because it's on the left side of the periodic table. What does the magnesium react with when it is burning? It's burning with oxygen in the air. What type of element is magnesium reacting with? Oxygen, but oxygen is a nonmetal. The melting point of magnesium oxide is 2,852 degrees Celsius, which is 5,166 degrees Fahrenheit. Why do you think the melting point is so high? That is extremely high. Like your oven maybe goes to like 450 Fahrenheit, maybe 500. That's 10 times what your oven can get to. Why do you think the melting point is so high? Well, you might have said a lot of different things, but at the end of the day, the magnesium oxide bond must be very strong. Now, why is it so strong? Oh gosh, I went all the way up. How did that happen? Yeah, MgO bonds must be very strong. Why do you think it's so strong? I don't know. Yeah, hopefully you give a better answer than I'm giving. Magnesium is a malleable metal, whereas the white magnesium oxide is very brittle. What do you think makes the structure strong in the sense it doesn't melt easily, but so weak in the sense that it crumbles at a touch? I mean, I'm asking what you think. So there's no wrong answer to what you think. You might be wrong in the sense of facts, but you're allowed to think wrong things. Nothing wrong with making mistakes. So let's see. I said they were very strong, so maybe the bonds are so strong that they can't bend. Question mark? You know, like glass is brittle, but glass is strong too. Like there are glass tables and stuff, you know. There's like glass bottom boats that you can like go in and look down through the bottom of the boat. So glass can be strong. It just can't bend. Let's read about ionic crystals and maybe we can answer some of these lingering questions we still have. Chemists have studied reactions of unstable atoms on the periodic table for hundreds of years. One of the first types of reactions to be observed was the reaction between metals and nonmetals. When a metal is brought into contact with a nonmetal, there's often a flaming or explosive reaction that is exciting and sometimes dangerous. When a metal reacts with a nonmetal, an ionic crystal is always produced. The most well-known example is ordinary table salt, or sodium chloride, which is produced when sodium metal is exposed to chlorine gas. Sodium and chlorine have very different electronegativities. That seems important. Since chlorine's electronegativity is so high, whereas sodium's electronegativity is so low, chlorine is able to take electrons away from sodium. This transferring of electrons allows both elements to obtain full valence shells. Remember, that's the octet rule. This is true for virtually all reactions of metals and nonmetals. Since all metals tend to have low electronegativities and nonmetals tend to have high electronegativities. Because the metals, sodium in this example, lose electrons, they develop a positive charge and are called cations. Since the nonmetals gain electrons, they develop a negative charge and are called anions. What's this diagram show? Highly magnified images of sodium chloride salt crystals. They look like sugar cubes or dice or something. The sodium cation Na+ is held in place next to the chloride anion Cl- by electrostatic attraction. This does not conduct electricity because the cations and anions cannot move. So here we've got our sodium ions, which are the purple ones. They've lost an electron, so they're smaller. And then chlorine has gained an electron, so it's the green ones. Notice they're very organized. It like repeats, you know. chlorine, or sodium chlorine, sodium chlorine, sodium chlorine, plus minus, plus minus, plus minus, plus minus. When dissolved in water, the crystal dissociates into the cation and anion. This conducts electricity because the charged cations and anions freely move around. While each reaction of metals and nonmetals produces a different crystal made up of different elements, all ionic crystals have several similarities. First, each crystal is highly stable and non-reactive, indicating that all the atoms in the crystal have a full outer shell of valence electrons, obeying the octet rule. Second, each crystal is made up of two parts, a cation plus and anion minus. Since the crystals are made of two types of ions, they are called ionic crystals. Cations and anions are held firmly in place inside the ionic crystal by electrostatic attraction between positive and negative charges. Since positive cations are always next to negative anions, the crystal forms a regular pattern structure known as a crystalline lattice. Ionic compounds are always solids because the forces between ions are so strong. I guess maybe that's why the bond is strong, because it has ions that are attracting. The temperature that ionic compounds melt at, melting point, is extremely high due to these strong forces. When an ionic compound does melt, the bonds between ions are broken. Third, each crystal conducts electricity only when it is dissolved in water or melted. A compound will conduct electricity if a charged particle, such as an electron, cation, or anion, is free to move and carry an electric current. When an ionic crystal is dissolved in water or melted, the cation and anion dissociate or break apart, which allows them to move freely and therefore conduct electricity. Solid ionic crystals do not conduct electricity because the cations and anions are locked in place in the crystal lattice structure. It's a good word, dissociate. If you ever need to break up with someone, you should use that. You should be like, I think we need to dissociate. And then they'll be like, what? And you'd be like, that's why. And just shake your head and walk away. Anyway, don't say I never helped you. Alright, I got a fill in the blank here. You should be able to fill in all these blanks based off of what you read and based off the criteria that you've learned. So go ahead and take some time on your own first. See if you can use your own brain before relying on your partners, but then go ahead and compare with each other and then go over it whole class. Let's go over this. An ionic crystal is produced when a metal reacts with a nonmetal. The crystal is made up of a cation and an anion that are held together by electrostatic attraction. When the ionic crystal is dissolved in water, it breaks up, dissociates into cations and anions, which causes it to conduct electricity. The crystal is formed when electrons are transferred. I spelled that wrong. From the metal to the nonmetal. The metal has a low electronegativity, so it loses its electrons, creating a positively charged cation, which is kind of a redundant thing to say because cations are always positive, but I'm putting it there more for your benefit so that you remember that cations are positive. The nonmetal has a high electronegativity, so it gains electrons, creating a negatively charged anion. This occurs so that both the metal cation and the nonmetal anion have full valence shells, or an octet. So how might ionic compounds be used in a phone, do you think? Remember, that's what we started this unit with. We looked at some pictures of phones, or maybe you threw yours on the ground before I was able to stop you, and you looked inside. So what do you think ionic compounds might be doing in a phone? Go ahead and pause. Discuss about it for a while. Can you make any guesses? Well, it turns out the transferring of electrons is basically creating electricity. So through some very clever engineering, scientists have actually been able to use ionic compounds in the batteries. Because what happens is one end of the battery has the metals, and they give away their electrons, and then the other end of the battery has the nonmetals, and they take the electrons. But they separate them so that they can't give the electrons directly. Instead, what happens is the electrons go through a wire to get from the metal to the nonmetal, And as the electron does that, it powers the phone because the electrons are moving and creating electricity. And then when you charge your phone, it forces the electrons to go back the opposite direction. It's a little more complicated than that, but for our purposes, I think that's enough of a connection. It's kind of interesting. So ionic compounds are used in the battery to create electricity. There's some other places as well, like the glass and things like that. But that's even more complicated to explain, even though this one was a very simplified explanation already. Let's look at conductivity of ionic compounds. We read about it. I don't know if you remember. You can always look back. But in order for something to conduct electricity, positive or negative charges must be able to move. Typically, these moving charges will be in the form of electrons, cations, or anions. So let's look at the conductivity of sodium chloride, an ionic compound. So I have 3 videos for you. One where the sodium chloride is dry, one where the sodium chloride is dissolved, and one where the sodium chloride is molten, which is actually melted. I think they also test it while it's dry first. So you might see that multiple times. So record whether it conducts or not, explain what the cations and anions are doing, and then pick which model goes with which situation. So like which of these is a dry sodium chloride, which of these is melted, and which of these is dissolved. So go ahead and do all of that, and then when you're ready, when you're done with the page, you can unpause the video and go over it with me. So did it conduct while dry? No. Did it conduct while dissolved? Yes. Did it conduct while molten? Yes. So dry cations and anions are locked in place in the crystal lattice and cannot move. Dissolved cations and anions are dissociated and wandering in the water. Molten cations and anions are also dissociated and sliding around each other, I guess, because they're a liquid. So dry would be model A, dissolved would be model C, because it's got water in between, and then molten would be model B, because they're just kind of chaotically moving around there. All right. So based on your knowledge of ions, name each ionic compound and construct a drawing and description that accounts for the formation of each crystal below. Your model should clearly show the behavior of electrons and show how each atom gets a full shell, indicate the formula of each compound. Here's an example one. So let's look at the model first. So they're drawing Lewis dot structures. Beryllium has 4 electrons, but only 2 of them are valence electrons, so it's just got 2 dots. Chlorine has 7 valence electrons, so it has 7 dots. The beryllium has a low electronegativity, so they're drawing the chlorine taking those electrons. Beryllium has to lose all of its electrons in order to get a full shell underneath, so you need 2 chlorines, because each chlorine can only take 1, because chlorine already has 7. To get an octet, it only needs 1 more. So in the end, beryllium forms a 2+ charge, whereas chlorine forms a 1- charge, but there's 2 of them. So there's a subscript of 2 down here. In our description, you want to talk about these 4 things: electronegativity, electrons, ions, and structure. So beryllium has a low electronegativity, whereas chlorine has a high electronegativity. Beryllium will lose its 2 valence electrons, forming a +2 cation, while 2 chlorine atoms each gain an electron, forming -1 anions. The 2 ions then attract each other through the electromagnetic force, forming a crystal lattice. So there's the 4 things we were supposed to talk about: electronegativity, electrons, ions, and structure. The formula would be Be, but there's only 1, so no subscript. Cl, but there's 2 of them, so we put a 2 as a subscript, which is the little number down there. All right, so I've got a whole bunch of practice questions. There's 5 of them. You should be able to, not easily, but up through number 4, I think is pretty fair to do, possibly just in partners or on your own. Number 5 is a little harder. I think most of you can probably get it by the time you go through number 4. But here's what I'd recommend. Do 2, 3, and 4. And then, maybe unpause after 2. Go through that one with me after you've tried it for a bit. And then give an extended time for 3 and 4, maybe like 10 minutes. And then you can unpause and go through that. And then depending on how people are feeling and depending on how much time's left in the period, you could maybe do number 5. But when you unpause the video, I'm going to start going through all of them, and I'm just going to go through all of them. Alright, sodium with chlorine. So let's draw it first. I actually found a tablet. I think it's only going to slightly help my penmanship, but let's see what happens. So sodium is Na, chlorine is Cl. Sodium only has 1 valence electron, whereas chlorine has 7. So that would be the before bonding. Copy paste that. For the during bonding, we're going to draw sodium giving its electron to chlorine. Remember, because chlorine has a high electronegativity. And then in the end, sodium's going to form a positive charge, whereas chlorine now has all the electrons and is a negative charge. So now we need to explain it with the same criteria right here. So we're going to say sodium is a metal and has a low electronegativity. Chlorine is a nonmetal with a high electronegativity. Chlorine takes sodium's valence electron. This gives chlorine a -1 charge, making it an anion. Sodium forms a +1 cation. The ions then attract and create a crystal lattice. Right, so that is the electronegativity, electrons, ions, and structure. There we go. Aluminum reacts with iodine. Where'd my pen go? Alright, so aluminum would be Al. It has 3 valence electrons. Iodine has 7, so 1, 2, 3, 4, 5, 6, 7. So here, aluminum has 3 to give away. Iodine can only take 1. So for the during bonding, what I'm going to do, let's move this a little, is I'm going to do 3 iodines. Let's move it a little more. Let's color code this, make it a little easier to see because there's a lot going on now. So aluminum has to give away all its electrons, but that iodine can only take 1. But this iodine can take 1, and this iodine can take another 1. And so what you get is in the end you have aluminum having lost all of its electrons. Now it has 3 more protons than it does electron. Iodine just gained the 1, giving a negative charge, but there are 3 iodines. I put the brackets to indicate that there are 3 I minuses as opposed to 1 I3 that has a -1 charge. Our explanation is going to be very similar. Aluminum is a metal with a low electronegativity, whereas iodine is a nonmetal with a high electronegativity. The high electronegativity iodine takes electrons from aluminum. Each iodine each of 3, let's say that, so we know how many there are. Each of 3 iodines gains 1 electron, and aluminum loses all 3 of its valence electrons. That was fine. Aluminum forms a +3 cation, and iodine forms -1 anions. The ions attract and make a crystal lattice. Lithium reacts with phosphorus. That's going to give you lithium phosphide. So lithium has 1 valence electron. Phosphorus has 5. 1, 2, 3, 4, 5. So lithium's going to have to lose this one. Phosphorus is going to have to gain 3. So just like before, we're going to have more lithiums because lithium can only give away 1. And I'll color code this again. So this electron goes here, this one goes here, and this one goes here. So in the end, we've got lithium is a positive charge, but there are 3 of them. There we go. And phosphorus gained 3 electrons, so it's 3 minus. But there's no subscript because there's only 1 of them. Once again, lithium is a metal and has a low electronegativity. Activity, meaning it is bad at attracting electrons. Delete that. Phosphorus is a nonmetal with a high electronegativity. Phosphorus takes 1 electron each from 3 different lithium atoms. This gives phosphorus a -3 charge and lithium a +1 charge. The ions attract and make a crystal lattice. Am I spelling this wrong? Where's my periodic table? Oh, my 3-year-old stole it. She just wants to be a chemist. Oh, here, she put it over there. Phosphorus. Oh, yeah. So I guess phosphorus in the sense of glowing is spelled differently than phosphorus, the element itself. You know, I always thought they were the same. Well, thank you very much, computer, for telling me. Let's look at aluminum and oxygen. All right, so aluminum has 3 valence electrons. Oxygen has 6, so 1, 2, 3, 4, 5, 6. So if I start trying to bond these together, you know, I could have just copied and pasted them. Oh, what am I doing? Try to bond these together. Aluminum fills up oxygen pretty quickly. So the oxygen's good now. But aluminum still needs to give away this last electron. So I'm going to add another oxygen. And aluminum can give that away. So all good. But the problem is this oxygen doesn't have a full octet. And so I can add another aluminum. And so now this aluminum can give an electron to oxygen. But now that aluminum doesn't have an octet because it still has these 2 electrons hanging around. Oh, so frustrating. So I just throw my hands up in the air and I give up. No. No. All you need is 1 more oxygen. Because now oxygen needs 2, and this aluminum has 2 more to give. So bing, bang, boom. There you go. So now aluminum, there are 2 of them, but they've each lost 3 electrons. And oxygen has each gained 2. I forgot to put the subscript. There's 2 aluminums and there's 3 oxygens. So that would be your formula. Aluminum is a metal and will lose its electrons due to having a low electronegativity. Oxygen gains those electrons because oxygen has a high electronegativity. Specifically, 2 aluminum atoms each give 3 electrons to 3 oxygen atoms. I'm going to put a colon here to clarify. Oxygen gains 2 electrons each. Aluminum forms a +3 cation, and oxygen forms -2 anions. I guess I need the cations to be plural, not A. Forms +3 cations, and oxygen forms -2 anions. The ions bond in a crystal lattice. Nice, there we go. So that's ionic bonding. Let's start talking about something a little different. This is not ionic bonding. We're going to talk about plastic. Plastic is a pretty important component of phones. Sometimes more of the top of the line phones try to make it seem like there's not as much plastic, but if you crack it open, that thing's full of plastic. All that green motherboard stuff, all the gray stuff, it's made of plastic. So plastic is an extremely useful chemical. It's created from crude oil, so the same stuff they make gasoline out of, they make plastic out of, and it's processed in a way where the atoms form very large molecules. Molecules are groups of atoms. The elements that make up plastics are almost always nonmetals. They're most commonly carbon, hydrogen, nitrogen, and oxygen. One of the simplest types of plastic is called polyethylene. It's also called polythene, but that's much less common of a name. It's made up of a repeating pattern of 1 carbon bonded to 2 hydrogens. So here it's actually only carbon and hydrogen. This pattern can be repeated hundreds or thousands of times before the atoms are no longer bonded to each other. So here's an example diagram. It's just CH, 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 CH. Each of these dashes are little bonds. And so basically this repeats just for thousands of times. Almost all plastics do not conduct electricity well and will melt when heated. Go ahead through these. When you're ready, you can unpause the video and I'll go through them. But this is supposed to be like an investigation. So I may not give you a super clear answer, but I want you to kind of think for yourself first. Number 1, given that most plastics do not conduct electricity, what can you conclude about the movement of charges in the compound? Charges cannot move. If there were moving charges, electricity would be able to conduct. Given the melting point is relatively low, what can you conclude about the strengths of the bonds between the plastic molecules? The plastic molecules must not be bonded that strongly to each other. Remember, ionic has thousands of degree melting points. Like ionic bonds you throw in a fire, it doesn't even melt if it's just like a normal fire, like a campfire or whatever. Number 3, what do you think the dashes represent in the model of polyethylene above? I think I actually said it when I was reading the background to you. But they represent bonds. But, like, what's in the bonds? What are the bonds? That I'm not going to tell you right now. but I'd be curious to, maybe you could pause it again and talk about that. So like, yes, the dashes are bonds, but what does that mean? Why do you think plastic is used in phones? Well, there's a lot of reasons. Plastic is cheap, it's moldable, it's chemically stable, like it's not going to rot or anything. It's an insulator, so it doesn't conduct, which you need some parts of the phone not to conduct, otherwise it would just like short circuit. Like if you drop it in the ocean, the phone just breaks because electrons go where they're not supposed to go. I don't know, there's probably other reasons that you came up with, but there's 4. Let's read about covalent molecules. A nonmetal plus a nonmetal gives you a covalent molecule. When a nonmetal reacts with another nonmetal, both atoms have a high electronegativity. Since they both strongly attract electrons, neither element loses electrons. Instead, the electrons are shared in a covalent bond. Covalent bonds do not cause crystals, rather they create small groups of atoms called molecules. Let's underline this part up here too. They both have a high electronegativity. The molecules held together because the positive nucleus in each atom is attracted to the negative electrons shared between them. Molecules are not repeating patterns like crystals. They are a small set of atoms bonded together. Since molecules usually don't attract each other that well, covalent compounds tend to melt easily, and many are liquids and gases at room temperature. Since the electrons are shared between the nonmetal atoms, electrons cannot move around, and so covalent compounds typically do not conduct electricity. Let's do melt easily as well. For example, fluorine is a highly electronegative atom. Here we have 2 fluorine atoms with 7 valence electrons. When 2 fluorine atoms react, each fluorine atom shares 1 electron with the other so that both atoms achieve a full shell. So that's what this is showing right here. These are the shared electrons. So these ones are on the shells of both fluorines. So like they count for the fluorine on the left, and they also count for the fluorine on the right. Together they create a fluorine molecule, F2. It is important to note that neither fluorine atom has a charge, since neither gained or lost an electron. The positive nucleus of each fluorine atom is attracted to the 2 electrons shared between them. The unshared pairs of electrons are called lone pairs. The fluorine molecule contains a total of 6 lone pairs. So 1, 2, 3, 4, 5, 6. Another example is a water molecule. Both hydrogen atoms have 1 valence electron, while the oxygen atom has 6 valence electrons. When they share electrons, hydrogen achieves a full shell of 2 electrons. Remember, it only needs 2 to get a full shell because it only has 1. While oxygen achieves a full shell of 8 electrons. Since both hydrogen and oxygen atoms share electrons, the atoms are tightly bound together in a covalent bond, but the atoms do not become ions with charges. So you can see what's happening in the diagram here. The oxygen's getting its 2 electrons it needs, and the hydrogen, they're each getting their 1 electron they need to have full shells. The elements hydrogen, nitrogen, oxygen, fluorine, chlorine, and bromine, and iodine form covalent bonds with themselves because they have such high electronegativities that they cannot exist as single atoms in nature. These are called diatomic molecules because they consist of 2 atoms each. The prefix di means 2. You need to memorize which ones are diatomic, because in later units, like if I say oxygen, you just have to know oxygen is O2. Same thing with chlorine and whatnot. So there's 2 ways that you can memorize this kind of easily. One is based off their position on the periodic table. Here we go. So if you look on the periodic table, hydrogen's over here, but then the rest of them form this kind of shape right here. They're all the really electronegativity atoms, the ones with the highest electronegativities. So hydrogen and then these ones are all diatomic. The other way that you can memorize it is a little mnemonic device. Have no fear of ice cold beverages. Let's say beverages. So have no fear of ice cold beverages. That's the 7 diatomics the HNFOCB, beverages. Alright, let's keep going. Covalent Lewis dot structure practice. This is kind of like we did for ionic, but now we're looking at covalent. Based on your knowledge of nonmetals, name each covalent compound and construct a drawing and description that accounts for the formation of each molecule below. Your model should clearly show the behavior of electrons and show how each atom gets a full shell. Diagram describe what's happening in the bond in O2. So that's oxygen. So we have 6 valence electrons each. I'm noticing the arrows are meeting in the middle here. So the arrows, they're not transferring electrons, they're just meeting in the middle. And then it looks like each pair became a bond. So 2 dashes is a total of 4 electrons. So there's 8 electrons around oxygen, 8 electrons around this oxygen, because remember, these count for both atoms. Same 4 elements as with ionic, if you remember: electronegativity, electrons, ions, and structure. Oxygen has a relatively high electronegativity. When 2 oxygen atoms bond, since they both have high electronegativity, they will share electrons. Each oxygen atom shares 2 electrons with the other to form a double covalent bond. Since no electrons were gained or lost, there are no ions present. The atoms bond to form a molecule. Let's see if we can find all of that. So high electronegativity right there is talking about electronegativity. They will share electrons. That's the electron behavior. They form a double covalent bond. That's also electron behavior. Since no electrons were gained or lost, there are no ions present. And then the structure is a molecule. So let's try this one. Diagram describe what's happening in the bond in CF4. Try it on your own first, but I'll give you a tip. Carbon kind of gets around, if you know what I mean, because it has 4 valence electrons, and so it needs 4 valence electrons to get to 8. That's a lot of bonds. So my recommendation is to put carbon in the middle of your Lewis dot structure drawing before you start moving electrons around. And then remember, for covalent bonding, your electrons need to meet in the middle. So go ahead and try this on your own, and then pair up, and then you can go over the video. There's a couple more practice questions on the next page as well. Alright, let's draw this. Carbon tetrafluoride. So we put carbon in the middle. And carbon has 4 valence electrons. And then we'll put fluorine on all sides. And fluorine has 7. So 1, 2, 3, 4, 5, 6, 7. And then you just select that and copy paste it and just put it all the way around your carbon. Don't you wish you could do this on paper? Where you just like copy and paste. Boom. And so now we need to start bonding things. Fluorine can only make 1 bond. So if I bond any of the fluorines to each other, they're done. And then it's not 1 molecule, it's multiple molecules. So what I have to do is I have to bond the fluorine to the carbon. So I can do 1 there, 1 there. Notice how I'm having the arrows meet in the middle? Because the electrons are being shared. So it's not that fluorine is giving an electron to carbon, it's they're both kind of giving an electron to each other. And so in the end, you've got carbon surrounded by fluorines, but each fluorine shares a pair with carbon. So we do a dash to represent a pair of electrons. Remember, this is 2 electrons, not 1. And then fluorine has a lot of lone pairs. Because these lone pairs, they didn't do anything. They just kind of watched. They're like your friend who watches you get prom dates and stuff and just is too nervous to ask anybody out. Come on, just ask for those digits, people. Put yourself out there. Alright, so I'm just going to copy paste this into the notes. I'm going to delete this table so that my picture fits more easily. I think I paused the video last time while doing all this, but you guys are getting to see the magic now. You kind of wish you paused the video, didn't you? Like, that I paused the video, I mean. Alright, so let's explain it. So carbon and fluorine are both nonmetals and have high electronegativity. The carbon atom shares 1 electron each with 4 fluorine atoms, forming 4 single covalent bonds. There are no ions present because no electrons were gained or lost, and the atoms form a molecule. There we go. What is the difference between a molecule and an atom? Do it on your own first if you haven't. An atom is the smallest piece of an element. A molecule is a group of atoms bonded to each other. Basically, a molecule is made of atoms. So molecules are always bigger. Diagram describe the bonding present in HCN, hydrogen cyanide. This stuff is extremely poisonous, by the way, so there shouldn't even be any of this chemical around you ever. Go ahead and work on it on your own first, then pair up, and then you can unpause for the answer. So let's draw this. Just like before, let's put carbon in the middle, because remember, carbon gets around, it makes a lot of bonds. And then we'll just put the hydrogen and the nitrogen on either side. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5. And then that's your before bonding. You just copy paste that into your during bonding. And then let's start bonding things up. The hydrogen, I can bond it to the carbon, and then hydrogen's good. Remember, hydrogen only needs 2 electrons to be stable, so the hydrogen's good now. The carbon and nitrogen, I can make a bond here, but the carbon still needs to make 2 bonds. The nitrogen also needs to make 2 bonds, so you know what I can do is I can just bond 3 times, and so now what I've got is I've got carbon with 1 bond to hydrogen, and then 3 bonds to nitrogen, and then nitrogen just has these 2 valence electrons, that one lone pair there, just kind of hanging around. As far as our explanation go, we can say all the atoms present, hydrogen, carbon, and nitrogen, are nonmetals. Therefore, their electronegativities are high. Carbon shares 1 electron with hydrogen and 3 with nitrogen. There is a single covalent bond between the hydrogen and carbon, and a triple covalent bond between the carbon and nitrogen. Since no electrons were gained or lost, there are no ions. The structure is a molecule. And there's covalent bonding. Nice. Moving on to metals. This is the last part of Standard B. Learning about our 3 types of bonding: ionic, covalent, and metallic. So there's a little simulation. Go ahead and click that and take 5-10 minutes, kind of play around with it, and test the conductivity of various materials. What do you notice? So something you may have noticed, did you pause the video and actually try it? Pause the video. Well, something you may have noticed was that the metals all conducted electricity. And the things that weren't made of metals didn't conduct electricity. So let's kind of talk through why that is. Go ahead and work through these discussion questions. If you haven't already, pause the video and do it on your own first. What is necessary for material to conduct? Well, if you remember all the way back from when we were learning about ionic bonds, in order for a material to conduct electricity, charges must be able to move around freely. Charges can be ions or electrons. Describe the electronegativity of metals. Metals have low electronegativities. Why can I never spell this right? It's that extra I keep forgetting to type. I'm trying to type too fast, I think. Given your data and answers so far, create a model and explain why the metal was able to conduct electricity. This is up to you. I mean, whatever you did, in order to conduct electricity, charges need to be able to move around. So models need to show charges moving around somehow. I do want to kind of push you a little bit. If you just drew what we had already drawn for ionic, then it doesn't make sense because metals are solids. And that's kind of why it's weird. Because metals obviously have moving charges, but the metals also aren't moving because they're solids. Like solids, the atoms don't move. Like if the atoms moved, then it would just fall apart. So metals are not moving, but they are moving. What? Right? The charges are moving, but the metals themselves are not. So what's going on? As far as why would you use metals in a phone? Again, you could probably use lots of reasons, but one big reason is that for electronics to work, you need to conduct electricity. You know, they also don't melt that easily, and they can be strong and things like that. They're not going to snap. Let's read about metallic bonds. Metals behave very differently than ionic and covalent compounds. They conduct electricity in the solid state, meaning electrons can flow through metallic bonds without disrupting the compound structure. See, I guess, so electrons can move while still having the rest of it be a solid. If the compound structure is changed by bending or twisting a metal, the metallic bonds rearrange and the metal stays together. This is this malleable idea. Metals are essential to modern life and have found uses in electronics, structural engineering, transportation, cooking, and many other areas. Electrons are not very tightly bound to metals due to metals' low electronegativity and ionization energy. In a metallic bond, the valence electrons leave the metal atoms and wander around through the sample of metal. Because electrons are not locked into one specific area, they are sometimes called delocalized electrons, or a sea of electrons. When the metal atoms lose the valence electrons, the metal atoms become positively charged. These metal cations are attracted to the delocalized electrons through electromagnetic forces, forming a metallic bond. The atoms exist in a malleable solid structure as opposed to a crystal lattice or a molecule. What's going on in this diagram? Metal atoms lose valence electrons easily. That's the dots, I guess. And here are the delocalized electrons. So instead of specific dots, we just have dots all over the place. And since the dots are negative, because they're electrons, these positive cations are attracted to this field of negativeness. The mobility of the valence electrons leads to metal compounds' characteristic properties. Electricity is simply charges moving in a direction, and metals always have delocalized electrons, which can move around. When a metallic compound is bent, the metal cations are still always in the sea of electron and remain bound together. This is why metals are malleable and not brittle. And in this diagram, we have the electrons, the sea of electrons. Remember, these electrons are always moving around, but there's always attractive forces between the cations and the sea of electrons, so it keeps the cations from leaving the metal. All right, let's diagram a structure of pure sodium metal. I'm realizing I didn't give you an example, so let's do the first one together as an example, and then you can pause it and you can try the next two. So sodium. Sodium is bonding to itself if it's pure sodium metal, because they're not single atoms just floating around, otherwise it would be a gas like the noble gases. but there's literally millions and billions of sodium atoms. So I don't want to draw that many. So instead, I'm just going to do a few. So let's just do 4. 4 seems like a good number. But it wouldn't be wrong to do 5 or 6 or something like that. So that's my before. They have 1 valence electron each. And then I need to somehow show the electrons being delocalized. And honestly, there's multiple ways that I think this could work that I've seen people do. When I teach this in person, we have like a brainstorming session. I'm just going to show you the most common one. And then if you want, you guys can come up with a different one that you all agree to. But just make sure everyone agrees so that we kind of understand the same notation. So what I'm going to do is I'm just going to draw arrows kind of wiggling off in all sorts of directions, showing that the electrons are leaving. And so now I have sodium, but they've lost electrons, so they have positive charges. And then my electrons, I'm just going to draw randomly, still moving. So I've still got my dots, and the electrons are moving around. So there's my before, during, and after. All right, sodium has a low electronegativity since it is a metal. Therefore, the electrons leave the atom and become delocalized. Sodium forms a +1 cation. The structure is a malleable solid. So go ahead, pause the video and try number 2 and 3 and see how that goes before unpausing. Discuss with each other and discuss as a whole class. Maybe you can do some on the board. Let's go over this one. So pure magnesium metal. So this is going to be very similar to the sodium, except magnesium has 2 valence electrons instead of 3. I'm just going to do 3 this time. And we're going to show the electrons wandering off. They all have to wander off. All the valence does. Remember, magnesium has a lot more than just 2. There's a full shell underneath, but you've got to kind of uncover it by having those valence electrons leave. And so now magnesium has a 2+ charge. It's a cation, but it's a 2+. And we've got a total of 6 electrons flying around delocalized. 5, 6. Explanation is going to be almost exactly like the previous one. Magnesium is a metal with a low electronegativity. Electrons become delocalized, and the magnesium forms a +2 cation. The cations form a malleable solid structure. Diagram and explain the bonding present in brass. So brass is a metal alloy of copper and zinc. Assume 1 valence electron each. Yeah, because they're transition metals, so you can't just look up the electrons easily, but the most common state that they're in, they just give away 1 each. So let's just do 2 of each, 2 coppers and 2 zincs. So I'll do Cu with 1 valence, zinc with 1 valence, and then like that. And then they all have low electronegativities. So what's going to happen to the electrons? The electrons, that's right, are going to fly off. They're going to be delocalized. And so in the end, copper and zinc both form +1 charges. So Cu plus, Zn plus, Zn plus, Cu plus. And we've got our 4 valence electrons just wandering around, delocalized, no home for them. Copper and zinc are metals, and would you have guessed it? With low electronegativities. Oh my gosh, not electrotitties. Electronegativities. What happens to the electrons? The electrons become delocalized, and both metals form +1 cations. The structure is a malleable solid. There we go, and that's metals. So now we've gone through metallic bonding, ionic bonding, and covalent bonding. So I'd like to do a little review and try to put in, kind of all in one place, the different properties we've learned. So remember, the elements on the periodic table are either found on Earth as pure elements or as compounds. The pure elements are found only bonded to themselves. Most elements are found as compounds, though, where different elements have bonded together. In this activity, you will sort through 9 different compounds. So use the information below to sort compounds into ionic, covalent, and metallic compounds. So based off the formula, based off the melting point, conductivity, etc., figure out which ones are which. And then once you've done that, then create a summary. So based off the properties, which ones are made of metals, nonmetals, or both? What's the conductivity? What's the melting point? Pick one of these compounds as an example, and then put in any other notes that you need to. I don't know if you're going to necessarily have anything in here, but sometimes things come up as you're discussing. So go ahead and take some time. This is going to take a bit, but unpause when you're ready to check your answers as a whole class. All right. So ionic is going to be the Fe2O3. You know, this would be easier just to write the chemical name. So we got rust, we got table salt, and we got Epsom salts are the ionic ones. Covalent is going to be air, wood, that one's hard, and sugar. Metallic is going to be the paperclip, the screw, and the aluminum foil. Highlight all that red. Alright, so ionic is made of metals and nonmetals, with 1 or 2 extremely rare exceptions that I'm not teaching you. Covalent is made of nonmetals, and metallic, shockingly, is made of metal. Ionic only conducts when dissolved or melted. Covalent never conducts, at least almost never, and metallic always conducts. Ionic have very high melting points. Covalent are usually low, and metallic is in between ionic and covalent. In general, could you find one ionic that melts before a metallic does? Probably, but they're not very common. Like 99% of ionics are going to melt after a metallic does, and then same thing, covalent is almost always going to melt first of the 3. Example compounds, you can just pick any one of these. So like the ionic, sodium chloride, that's a metal and nonmetal. Covalent, we had the air, which was mostly nitrogen and oxygen. And then metallic, we have, iron or What was the paperclip made of? Mostly iron, so Fe. Any other information? Maybe. I don't know. There are exceptions, like wood doesn't melt, it burns instead. I actually watched a video. You can kind of melt it, but you have to cheat. You have to do it when there's no air, and then you can't do it with fire. You just have to like move the wood really fast. Alright, I got one more thing of practice for you. 2 pages, I guess. But go ahead and work on this, and then when you're ready to go through it, you can unpause. Write down everything you know about each type of bonding. Well, we kind of just did that on the previous page, but ionic is metals and nonmetals. Strong bond, high melting point, conducts only when dissolved or melted, made of ions. What else? Crystal lattice, high and low electronegativity. Metallic is metals. Medium strength bond, always conducts. Ions in a sea of electrons. We can say metal cations in a sea of electrons. Malleable solid structure, low electronegativity. Covalent nonmetals, low bond strength, at least between the molecules. Inside the molecule is actually quite strong, but like between the 2 groups of atoms are very bad. Never conducts, at least almost never. We've got electrons being shared. Oh, let's add the electron behavior here too. Electrons are transferred. Well, we said sea of electrons here, I guess. So delocalized electrons, though, we use our vocabulary. No ions. Molecule, high electronegativity. Diagram and describe the bonding that occurs between calcium and fluorine. No problem. Would love to. So we take calcium. Calcium has 2 valence electrons. Boom, boom. Fluorine has 7. And that's our before bonding. Our during bonding, I think I missed one for fluorine. I did. Fluorine needs to get an extra electron there. I'm actually going to need a whole nother second fluorine anyway, because calcium has to give away 2 electrons. Remember, this is ionic. And so we need a second fluorine because fluorine can only take 1. So I transfer 1 electron there, transfer another electron there. And so now I have Ca2 plus, fluorine minus, with a full shell. But there are 2 fluorines, so a subscript of 2. Our explanation is going to be very similar to all the explanations we did for ionic. So calcium is a metal with a low electronegativity. Fluorine is a nonmetal with a high electronegativity. Calcium gives 1 electron each to 2 fluorine atoms. The calcium forms a +2 cation, and the fluorines form -1 anions. The ions attract and form a crystal lattice. I feel like I used the word form a lot just now. Diagram and describe the bonding that occurs in nitrogen. No problem. You know our air is mostly nitrogen because nitrogen is bonded so strongly to itself, our body can't do anything to it, so it just goes in and out of our lungs. We'll see in a second why nitrogen is bonded so strongly, but something like oxygen isn't. So nitrogen has 5 valence electrons, and remember it's diatomic, so N2 each nitrogen needs to make 3 bonds, but they can't lose electrons because they're both really strong. So instead what happens is they're going to share 3 sets of electrons. So that's a total of 3 covalent bonds that the nitrogen's making. So 3 dashes, a total of 6 electrons being shared. And so this is why nitrogen is so strong, is because it's got a triple bond connecting the nitrogens to each other. The nitrogens are nonmetals and have high electronegativities. Therefore, electrons are shared. Each nitrogen shares 3 electrons with the other atom, making a triple covalent bond. There's some bacteria that can create that can break that bond. They're called nitrogen fixing bacteria, and then lightning can also do it. So when there's storms and stuff, sometimes you can smell that broken nitrogen. But it's very important because proteins are based off nitrogen. So if that nitrogen never got broken, we would not be able to live. But we can't break it ourselves. Bacteria has to do it for us. What was I saying? There are no ions present because no electrons were gained or lost, and the structure is a molecule. Fernando is given 4 different chemicals. He knows that they are likely either covalent ionic or metallic bonds. He decides to test them by heating them and by testing their conductivity when melted or dissolved. He collects the data below. Unknown A melts quickly, starts bubbling, smells acrid, which means basically it smells nasty, turns black, and produces smoke. It is not conductive, solid, or dissolved. B doesn't melt, seems to get a little darker, not conductive. When it's dissolved, it does conduct. C becomes liquid, but after continued heating, turns back to a solid that looks the same. It doesn't conduct as a solid, kind of conducts when dissolved. D turns red under heat, but quickly returns to original color after removal from heat, does not melt. It conducts as a solid, but does not dissolve, so we can't test it. Fernando decides that unknown C is a covalent bond. Since it became a liquid, he is wrong. Explain. Well, covalent bonds don't conduct. So why it became a liquid and then went back to a solid? It might have had water inside of it. Like sometimes ionic compounds will actually absorb water, and when they do that, you can drive the water off when you heat them. They're called hydrates. But anyway, unknown C cannot be covalent because covalent bonds don't conduct electricity, even when dissolved. I'm going to say also, if it was covalent, I would expect it to stay melted. I mean, there are exceptions, I suppose, but that's what we'd expect, right? What type of bonding is present in unknown D? Why is this type of bonding able to conduct as a solid? Include a model. So, conducts as a solid, I mean, that tells you right away it's metallic bonding, because that's the only one that conducts as a solid because it's got delocalized electrons. Unknown D must be metallic bonding because it conducts as a solid from the delocalized electrons. As far as a model, I'm just going to go up to the metallic bonding notes, and I'm just going to steal this one, because here I have the electrons being delocalized. But as long as you show the electrons being delocalized, I think you're good. What type of bonding is present in B and C? Why do they conduct only when dissolved? Include a model. Doesn't melt, melts but then doesn't. So conducting not as a solid but when dissolved means it's ionic, because ionic has that crystal lattice. They do not conduct as a solid because they are ionic bonds. The ions are locked in the crystal lattice and cannot move when solid. When dissolved, the ions dissociate and move freely, allowing the compound to conduct electricity. And as long as your model shows, the ions breaking apart and moving, then you're good. I'm going to go copy the one from the reading. So there you have it. And that's the end of the standard. Good luck on your quizzes, and I'll see you in Unit 4. Bye-bye.